Hey, I'm Stan, and in this video, I'm going to talk about some basic image reconstruction techniques that are used in computed tomography. So, we're first going to cover some basics, and then we'll move on to classical image reconstruction methods, iterative reconstruction, and artificial intelligence-based reconstruction algorithms. Finally, we'll look at the methods that are available within the Monash Health network. To reconstruct a CT image, we measure the transmission of X-rays through the patient at many different angles. But what does the radiation do inside the patient? Well, to understand image reconstruction in CT, we first need to know one of the most famous equations in radiation and medical physics, the exponential attenuation law. As an example, let's say we want to image the object shown on the left, which is a 4x4 matrix with each pixel having different attenuation coefficients. So we can take our exponential attenuation equation and we can discretize it so that it's no longer continuous. And when we reconstruct an image, we're really just creating a map of the attenuation coefficients that appear in this equation. And that's all that this is. It's just a map of attenuation coefficients. So we have our discretized exponential attenuation equation, in this case still for the 4x4 matrix, and we can measure the intensity of the beam as it leaves the X-ray tube, and we can also measure the intensity of the beam on the opposite side of the gantry after it has passed through the patient. Now, if we rearrange this equation, we can use our measurements to obtain projections. However, we know that an image of a patient is just a map of these attenuation coefficients. And we can see from the equation that a projection measures the sum of the product of attenuation coefficients and the size of each pixel. So how do we separate these attenuation coefficients so that we can generate our map? Well, this is the crux of the issue. CT image reconstruction essentially uses mathematical techniques to separate these coefficients. So if we start with just simple back projection, on the left we can see a set of parallel projections through a patient. Now for each projection, the sum of the products of attenuation coefficients and pixel sizes is measured. And this is measured for different projection lines through the patient and at a range of different angles. So in that middle image, what you can see is this process of simple back projection where each value is smeared along the projection line. And if you do repeat that for a high number of angles, you can obtain the reconstructed image on the right. And although the chest and lungs are visible, you can see this image is quite blurry. And this blurriness follows a 1/r pattern, and this is caused by the decreasing density of overlapping projections as you move radially outwards. So you should note that one of the key assumptions in simple back projection is that the measured signal is distributed evenly over the line of projection at each angle. So what you can see here is a dynamic visualization of the acquisition process of a CT image. So as a set of projections is obtained at each angle, this allows us to generate what is known as a sinogram. And this sinogram corresponds to our raw measurements. So to understand how we reconstruct images based off our sinograms, we have to understand a bit about mathematics. So we introduce three different domains. One of them is object space, which is our linear attenuation coefficient matrix, or our image. Now the second is radon space, which is our raw projection data, and this is the sinogram. Finally, we have to introduce Fourier space, which is derived from the 2D Fourier transform of object space. So clearly there are mathematical operations to go between these spaces. An important concept of image reconstruction is known as the projection slice theorem. This piece of mathematics essentially tells us that the 1D Fourier transform of a projection at a given angle gives the values of the 2D Fourier transform along a radial line at the same angle. So if we do this for all the projections at all the angles, we would be able to fill out our 2D Fourier space. In principle then, if we have the 2D Fourier transform of the image, we can take the inverse 2D Fourier transform and obtain our image. So in practice, why don't we do this? In principle, we could use our sinogram combined with the projection slice theorem to create our image in frequency space, and then take the 2D inverse Fourier transform to obtain our image. However, this doesn't produce the best result, as the rebinning of the Fourier transform projections and the interpolations required to obtain Cartesian coordinates are prone to introducing artifacts in the reconstructed images. Prior to the 2D inverse Fourier transform into image space, the regularly distributed points in the polar 2D Fourier space must be transformed to regularly distributed points in a Cartesian 2D Fourier space. The transformation from a polar coordinate system to a Cartesian one may lead to artifacts, since the sampling of the 2D Fourier space is much denser around the origin at lower frequencies, while it is sparser further away from the origin at the higher frequencies. So the improved way to reconstruct images is by using a technique known as filtered back projection, which consists of 4 steps. First, many 1D Fourier transforms are applied for each projection angle. Then, a high-pass filter is applied to each of these transform projections, preferentially keeping the high-frequency components of the transform projection. The next step is to apply the inverse Fourier transform to these filtered 1D Fourier transforms. So what we obtain is our radon space, or our sinogram, but with modified projection profiles. And now if we apply the back projection to those modified profiles, we obtain a better reconstruction of the object being imaged. As you can see in the example, the more projections are used, the better the image becomes. So to talk a bit more about the high-pass filter we're applying, the filtered back projection method applies this ramp filter in the frequency domain. And this ramp filter is just a linear filter which preferentially selects high-frequency components of projections. So when we reconstruct the image, we just back project these filtered projections. The filter that theoretically yields an optimal reconstruction is the so-called Remlach filter, which in the clinic is usually called the sharp or bone filter. This provides optimal spatial resolution in the reconstructed image, but also high noise levels. Often, filters are used that reduce noise levels in reconstructed images. A modest roll-off is achieved with the Shep-Logan filter, which provides images that are less noisy and provides a better low contrast resolution and slightly inferior spatial resolution in the reconstructed image. And we can see in this dynamic visualization how much better filtered back projection reconstructs images as compared to simple back projection. So we've covered filtered back projection and we've seen that different filters exist in this image reconstruction. Now we'll go over a clinical example. So osteoporosis is a disease that is characterized by low bone mass and microarchitectural deterioration of bone tissue, which leads to an increased risk of fragility fracture. Now, a recent study investigated the impact of CT reconstruction kernels on volumetric bone mineral density measurements, which are used to diagnose osteoporosis. And they found that smooth kernels, such as soft, chest, and detail, show minimal variation, whereas sharp kernels, such as the lung, bone, and edge ones, introduce large errors. So using internal calibration, the lung kernel overestimated volumetric bone mineral density at the L4 vertebra by 9.63% and underestimated it at the femur by 5.98%, which demonstrates the effect of sharpening on density values. And they found that these variations highlight the need for consistency in kernel selection when performing opportunistic CT analysis for osteoporosis screening. Filtered back projection is routinely used in clinic, but does suffer from a number of limitations. As back projection doesn't provide an exact reproduction of the original image, the projection operation results in non-uniform sampling and performs poorly when projection data contains significant noise. The filtered back projection methods must also be extended for a fan beam acquisition. The RAM filters amplify high-frequency components, potentially leading to artifacts, and in the case of limited projection angles, streaking artifacts are introduced, and image quality can be lower compared to other reconstruction methods. The filtered back projection method also does not lend itself well to low dose, imaging such as pediatrics, and the filtered back projection assumes that projections are perfect. So there is no beam hardening, scatter, or motion artifacts. And finally, filtered back projection is not directly applicable to cone beam CT or spiral acquisition CT. Now, let's look at an alternative solution for reconstruction. Other solutions include algebraic or iterative reconstruction, which can be used in CT. An algebraic reconstruction may seem attractive. However, algebraic reconstruction through equation solving is not feasible in clinical practice, owing to the large image sizes that is used, as well as inconsistencies in the equations from measurement errors and noise. Iterative or statistical reconstructions are now commonly used in CT. The iterative reconstruction is also routinely used in nuclear medicine. Iterative reconstruction techniques provide potential benefits, including the removal of streak artifacts and better performance in low-dose CT acquisitions. So, iterative techniques are becoming popular in commercial CT scanners and can produce low-noise images. So, in essence, the idea of iterative reconstruction is that if the CT image or an approximation is known, then the projection data can be computed using forward projection. So iterative reconstruction techniques go through a series of iterations in the process of CT reconstruction. So we begin with a guess of the image. The guess is then used to compute forward projection data sets, which are then compared with the measured projection data sets, or sinograms. The difference between the mathematical projections and the physical measured projections creates an error matrix. And then this error matrix is used to update the next iteration of the image. And this process continues until that error matrix is minimized. There is a balance between reconstructing the anatomical information and the presence of noise in the image. Different iterative algorithms use the error matrix to update the next iteration in a different manner. After a certain number of iterations, the estimated image becomes an excellent depiction of the object that was scanned. It's recognized that iterative algorithms can model many of the physical parameters that filtered back projection can't, such as the X-ray spectrum and blurring of the focal spot. So in principle, iterative algorithms can make better use of the acquired data by producing images with high signal to noise ratios at the same dose, or they can produce images of similar signal-to-noise ratios at lower doses. And as shown in the example on the right, using a lower dose, the image obtained has a better contrast-to-noise ratio. And all major CT manufacturers have implemented iterative reconstruction techniques on at least their newer scanners. However, this capability is often an optional feature. But because of the demonstrated benefit of potential dose reduction using such reconstruction techniques, reconstruction methods will gradually shift towards iterative ones in the clinic. Although iterative reconstruction methods are routinely used in the clinic, they do have limitations. So these methods require significant computational power and time compared to classical methods, such as filtered back projection. There are convergence issues where the iterative process may not always converge to a unique solution, especially when dealing with noisy or incomplete data. Poor parameter tuning can also lead to slow or unstable convergence. Iterative reconstruction also depends on initial conditions and priors. So reconstruction artifacts can be introduced if the algorithms are not properly tuned. And iterative methods can effectively reduce noise, but can also overly smooth images, potentially obscuring finer structures. And finally, there's a lack of standardization, so different manufacturers implement proprietary iterative techniques, making it difficult to standardize across systems. To overcome the limitation of image noise in the reconstruction process, iterative reconstruction methodologies were explored in the mid-2000s. However, even with advancements in computational power at the time, fully iterative model-based iterative reconstruction techniques were just too computationally intense to be used clinically. It took hours to days to produce a series of CT images. So the reason model-based iterative reconstruction methods initially took so long is because they account for both image noise properties and the geometry of the CT system. So these methods have been shown to reduce image noise, enhance object boundaries in the body, and reduce artifacts. So as a compromise, statistical-based iterative reconstruction algorithms were introduced to mix up the speed of filtered back projection with an iterative approach that reduces quantum noise in the image. So these statistical-based algorithms were highly effective at reducing image noise and widely adopted across all CT manufacturers. As computational speeds increased and statistical-based iterative reconstruction algorithms became more integrated into routine clinic, hybrid algorithms were introduced that blended noise reduction from statistical-based methods with some of the improvements seen in model-based iterative reconstruction methods. Now, although all this sounds great, applying iterative reconstruction led to images that appeared smoother and less pleasing to the eye. For several decades, radiologists became accustomed to the sharper object boundaries and the noise texture depicted in filtered back projected images, while iterative reconstruction was shown to adversely affect noise texture and smooth object boundaries. Iterative reconstruction introduced nonlinear effects such that image noise was spatially dependent and spatial resolution was contrast dependent. And you can see in this example how the iterative reconstruction gives a plastic or blotchy texture as compared to a less iteratively denoised image, which the radiologist would be more accustomed to. So finally, moving on to AI-based reconstructions, these are referred to as deep learning reconstruction algorithms, and they've introduced a new way to improve image quality without the penalty of increasing patient radiation dose or reconstruction time. Commercially available deep learning reconstruction algorithms use a deep convolutional neural network to recognize image noise patterns and remove these from the raw data or from an already reconstructed CT image. Critical to the success of any of these models is the training data sets employed to teach the algorithm to differentiate between noise and anatomical structure. In all cases, these algorithms are trained using pairwise data of low noise and high noise images. Through the training process, the selection of hyperparameters and node weights are tuned to maximize the consistency and accuracy of these reconstruction methods. Additionally, AI-based reconstruction times are nearly equivalent to those of statistical-based iterative reconstructions due to the innovation and deployment of GPU-enabled computers. There are many approaches to the use of deep learning reconstructions that have been explored in the scientific literature, but the two main ones that are purchased and used clinically are either a vendor-independent approach that operates in the image space, or a vendor-specific approach that operates in image space combined with projection space, meaning that the deep learning reconstruction algorithm has access to the raw sinogram data. All current versions of deep learning reconstructions come with multiple strengths or implementation level options. For example, Canon's algorithm is available for use on all body parts, whereas GE's method is only applicable to image reconstruction applied with the standard reconstruction kernel, so typically only applied for soft tissue reconstructions. So the first approach that we mentioned is primarily offered by third-party solutions that sit between the scanner and the PAC station. So the CT scan is performed and the data is then reconstructed using the algorithm of choice on that scanner. The CT scans are then sent to an independent server that will function to clean up the CT reconstructions using the vendor-specific software. Now, the second vendor-specific approach likewise functions to reduce image noise, but has been shown to also improve object edge definition and improve spatial resolution due to its access to raw projection space data. Now, all current versions of deep learning reconstruction algorithms come with their own individual strengths or implementation level options. So to understand a bit more about how these AI-based reconstructions work, you can think of them as neural networks that crudely model the neurons within the brain and the synaptic connections of those neurons. As with any learning process, the network architecture, or the connection of those neurons in the network, is important, but what's even more crucial is the training data that's used to model the network. Typically, ground truth training data are used to teach the network the properties of a CT image. Then noise is introduced into the data through simulation, for instance. In this manner, the network has paired examples of noisy and clean data. And the aim of the network is to learn a method to remove the noise from the data going between those two sets. So it has been shown that denoising can be achieved by training the network with multiple realizations of the same noise pattern in so-called noise-to-noise training, but this has not been yet clinically implemented. So to get more of a feel for how these models work, let's unpack this diagram a little bit. So first, let's say we have a patient that looks like this, and we image this patient using a CT scanner and we generate a high quality sinogram as normal. Let's say we either acquire the same scan again using different acquisition parameters, or we simulate and artificially generate noise and get a low quality noisy sinogram. So in doing this, we've now generated our paired data sets. Now, with our paired data set, we have our high quality sinogram, which we generated as normal. And then we can use our traditional reconstruction methods, or our gold standard, the best alternative method we have at hand, whether it be iterative reconstruction or filtered back projection. We use this and we generate our ground truth image, the CT scans that we clinically use. Now, if we go back to our low quality sinogram, okay, and we have this representing our network, and we can think of this as a black box. We don't have to understand exactly how this works, but the model, this deep learning model, essentially tries to go from the low quality sinogram to an output image. It tries to reconstruct. But because we have our ground truth image, we can compare the two. And we can see, oh, well, the AI generated image, the AI generated reconstruction is just not that good. And then we back propagate. So the network adapts and learns from essentially its mistakes to then go back and try to generate this image again and compare until it gets better. It iterates through this process until the AI reconstructed image from the low quality sinogram gets as close as possible to our gold standard. And this is essentially how these deep learning reconstructions work. And I'd also like to add, as I think it's an interesting point, that training these models requires a huge amount of number crunching, and the big computers or GPUs needed to undergo this training process cost quite a lot of money. So this process that we described of backpropagation describes the methods that we use to update the network coefficients during the learning process. This step is where image quality characteristics of ground truth images are encoded into the network that allow future sinogram data to pass through the network and inherit characteristics of the ground truth images that we use to train the network. So in practice, there are choices to be made about the selection of the clean or target training data, which affect the output of the network. Each CT vendor or third-party denoising vendor performs validation, testing, and quality assurance, after which network architectures are saved as a static software instance. Networks provide reproducible and stable results when used in the field. The process of using a deep learning network to reconstruct noisy data is referred to as inference. In the future, it may be possible for networks to learn in real time or to make network parameter adjustments tailored to specific patients. But all the current FDA-cleared methods use networks with locked weights. CT deep learning reconstruction algorithms have been shown to improve image quality by preserving object edge detection, reducing image noise, and enhancing diagnostic confidence for various diagnostic tasks. Noise is often the limiting factor when low contrast detectability is the primary diagnostic task. So the validation and characterization of image noise properties for deep learning reconstruction applications is critical. Deep learning reconstruction has nonlinear noise parameters, meaning that classical image quality metrics such as pixel noise, contrast to noise ratio, and SNR do not fully convey the impact of deep learning reconstructions on image noise. So Fourier-based image quality metrics such as noise power spectrum and contrast-dependent task-based modulation transfer functions have been used in characterizing noise, contrast, and resolution in CT when applied to classical reconstruction methods. All methods, whether filtered back projection, statistical, model-based, or deep learning, violate one or more assumptions for the use of Fourier-based image quality metrics. It's recommended to instead use task-based observer studies as the gold standard by which diagnostic efficacy, image quality, and dose reduction can be assessed for deep learning reconstruction in CT. Now, if we look at all of these reconstruction methods we've covered, filtered back projection is great because it allows us to obtain predictable results from scans of any imaging object or patient condition. While iterative methods assume that there are regions of the patient with low spatial frequency content over which aggressive noise reduction can be applied. This assumption means that noise reduction is higher in uniform regions relative to highly textured regions. This assumption means that these methods are then non-linear with object contrast, object background texture, and dose level. And advanced iterative reconstructions are similar, but have more advanced modeling of system noise properties and sampling geometry, which can allow for increased performance in noise reduction or spatial resolution. Model-based image reconstruction doesn't assume a point source for the focal spot, a point source for individual detector elements, or a monochromatic X-ray spectrum. So the model-based method accurately models photon statistics using raw projection data. Finally, the deep learning-based reconstructions assume that the scan data share feature characteristics with the data that was used to train the model. So they assume that we want the output of our reconstruction to match the data that was used to train the model. So images reconstructed using deep learning will have image quality characteristics matching those of the training data. So the potential for dose reduction using deep learning reconstruction has shown to be feasible down to 44 to 83%, while maintaining equivalent image quality and diagnostic confidence as compared to our iterative reconstruction or filtered back projection. But some of the limitations of deep learning reconstructions include generalizability and robustness issues, which is the case with any AI model, their handling of artifacts and stability. A major one is a lack of explainability and interpretability of the model outputs. There is, as previously mentioned, a computational complexity and so hardware requirements. There's also regulatory and safety concerns, which are a challenge in terms of clinical implementation. There's also a loss of physically meaningful constraints and a need for radiologist trust and acceptance of these images, as was also the case for iterative reconstruction images. And finally, workflow integration challenges and cost-related limitations. So at Monash Health, we have many sites and we have CT scanners from different manufacturers and different models. So we have scanners from GE, such as the Discovery, Revolution models, which have iterative reconstruction algorithms. Some have deep learning-based reconstructions, as well as advanced iterative reconstructions. We also have a range of scanners from Siemens at a range of different sites that have iterative reconstructions. Some have metal artifact reduction specific algorithms, as well as advanced iterative. We also have Canon CT scanners, which do feature deep learning based reconstructions as well as iterative. We also have some scanners from Philips, which have advanced iterative reconstructions. And finally, a scanner from Toshiba, now Canon, which uses filtered back projection. So to go over some of the key takeaways of this talk, CT image reconstruction is based on X-ray transmission data and attenuation coefficients. This is the essence of image reconstruction. Back projection results in a blurred image due to the assumptions made in distributing the projection data. Filtered back projection improves image quality relative to simple back projection by applying a high-pass filter before back projection. Radon space or sinograms and Fourier space are key domains in image reconstruction, with the Fourier slice theorem really enabling reconstruction methods. Iterative reconstruction refines estimates iteratively, reducing noise and artifacts, but also requires high computational power. AI-based deep learning reconstruction algorithms use neural networks to denoise images and reduce radiation dose. Filtered back projection is fast, but it amplifies noise and artifacts. Iterative reconstruction reduces noise, but is computationally expensive, while deep learning reconstruction balances image quality and speed. Deep learning reconstruction can achieve quite significant dose reductions between 40 and 80%, whilst maintaining diagnostic quality. Some of the challenges with implementation of deep learning reconstruction algorithms include interpretability, robustness, regulatory approval, and radiologist acceptance. AI-driven reconstruction methods are evolving and are expected to become more widely used in clinical practice. That's the end of this talk. I really hope that you found this in any way useful. And as always, if you have any questions, please get in touch. Thank you.